Hi everyone, my name is Hector Anapan Laval, and I'm going to present today the Retro Framework, which is the targeted resource management in multi-tenant distributed systems. So, what is the agenda for today? Apologize for that. So, what is the agenda for today? We're going to look at the introduction, overlooking the overview and the current issues in distributed systems and what this framework is trying to tackle. So we're also going to look at the Hadoop architecture overview. Uh, we're going to look at its components and the cluster flow, since this retro framework depends on, is based on the Hadoop framework. So we're going to also look at the motivations that and the challenges that are being looked at in order to use this retro framework in order to tackle these challenges and issues. So what is retro framework? We're going to also definitely look at that. We're going to understand what the proposed solution to these to the latter challenges are. The abstractions, the main abstractions of this framework, the system architecture, the design implementation, as well as the current policies. We're going to look at how this framework was evaluated and, of course, the results and its conclusion and the conclusions as well as my personal view of this paper. So the introduction. Today, shared distributed systems are shared by multiple tenants. Some types of these systems of these distributed systems are common storage, data analytics, database queuing, and coordination services. So multi-tenancy has obvious costs and computing advantages. But at the same time, it comes at a cost such as sharing fine-grained resources as well as resources across multiple processing machines. Also, the mismatch in this management granularity occurs when using traditional resource management mechanisms in the operating system as well as the hypervisor. Effective resource management is important in distributed systems. So in distributed systems shared by multiple tenants, this is actually a very important requirement in order to be able to provide the quality of service guarantees across tenants and systems. So apologize for that. So many systems lack performance isolation. They lack they experience contention, latency, and even outages. This is actually usually caused by aggressive or highly variable workloads. It's also caused by improperly throttled maintenance tasks such as data replication. So there is, we can see that based on these things, there is a need of a monitoring management like this retro framework solution that is able to handle and orchestrate these variable workloads in order to maintain system performance in a distributed system setup. So let's look at the Hadoop architecture. Let's look at its overview, since the retro framework is presented in the context of the Hadoop stack. So we'll go over I guess its components in order to better understand Retro's proposed solution and its architecture design in more detail, which we can see in the figure on the right. So some Hadoop components, we're going to be working with the Hadoop distributed file system, which is HDFS, Zookeeper, Yarn, MapReduce, and HBase. So we're going to go over what each of these components do as part of the cluster. So to the figure to the right, let's just define what each component do. Thus, so the green rectangles in this figure represent servers. The white rectangles represent processes, and the circles represent the control points, which is a big implementation as part of the retro framework. So the Hadoop components. Let's look at the HDFS, the Hadoop Distributed File System. Uh, it basically consists of a master-slaves approach. So the master is called the name node, and the slaves are called the data nodes. So the data nodes store replicated file blocks for reliability purposes, and they run in each worker machine, each slave machine, while the name node, which is the master node, manages the system file data and makes sure of the health of its data nodes. There can be also in this approach a secondary name node to back up the current state of the main name node. So we're going to look at the yarn, which is the yet another resource negotiator, which is part of the Hadoop package. So it consists of a resource manager and a node manager for each worker node. So, and it also contains something called Hadoop MapReduce, which is an application of Yarn. MapReduce runs its processes, which are the application manager and the MapReduce task, inside the Yarn containers managed by the name nodes. So also we're gonna see what HBase is. Is actually a data store running on top of HDFS. HBase consists of region servers, RS, on all workers, and an HBase master, which is usually co-located along the name node of Yarn. Also, Zookeeper, which is the distributed coordination system used by HBase. So what is the cluster flow here? The MapReduce job input and the output files are fetched from HDFS or HBase, either one. So the advantage of doing so is for reliability purposes. Basically, during the job shuffle and join phase, which are in between the map and reduce tasks, the intermediate output produced by this phase is written to the local disk by mappers. Then this output is read and transferred by the node managers to the reducers. So for the case of HBase, the query is executed from one region server and reads and writes data from one to many or many data nodes. So what are some motivations that cause the retro framework to be come up with? So one of them is the race conditions between tenant requests as well as system tasks, such as some example of system tasks could be, for example, garbage collection or data replication. So this bottleneck culprit can actually be unpredictable. The dependencies such as input workload, the workload of other tenants, the overall state of the system, and performance characteristics of underlying resources. So the figure on the right shows how a simple disk read request, which is letter I, as we see on the legend to the right, it can be actually strongly impacted by other concurrent tasks. So we can see in the figure that letter I is the client request to read the disk, which we just explained. Double I is the disk operation, which is the latency of data node disk operations. The Q is the latency at the name node RPC queue, and the last one would be the lock operation, which is the latency to acquire the name node quote-unquote name system lock. So more motivations. We're gonna look at we're gonna see what this means, right? So any resource can become a bottleneck. So the workload of one client can affect other concurrent requests, which in turn causes concurrent resource requests. And as explained in the first example of resource bottlenecks in the previous slide, a simple this read request can be adversely affected by latency due to other clients' requests or requests coming from systems or available resources. So multiple granularities of resource sharing, that's definitely a big item to look at when it comes to distributed systems. There has to be a balance between fine-grained granularities and coarse-grained granularities. So also maintenance and failure recovery, it causes congestion. Let's say background tasks compete for the same resource, and too many background tasks affect performance of the actual foreground tasks. So also resource management does not exist or is incomprehensive in present distributed files, distributed systems. For example, there's no mission control policies on distributed systems. Also, aggressive jobs can overload resources not being monitored, such as network resource, disk resource, etc. So what is this proposed solution that this paper is talking about? It's, they have called it the retro framework. And its main goal is to enable simple and targeted resource management policies for multi-tenant systems. These policies will be discussed previously in motivation, will be tackled by this framework. What is its core principle? It's to separate resource management policies from mechanisms required to implement them. So this will be explained further in the further slides. So what are the main abstractions of this retro architecture design? The three important ones are workflows, resources, and control points. So let's start talking about the workflow abstraction. It basically is a set of requests that consists of resource management factors. For example, a workflow can be, let's say, a collection of all background activities. And each workflow it has a unique ID throughout the execution path of all its requests. Sorry. So let's talk about resources. What happens here is that it treats all resources uniformly under a common abstraction for dynamic and elastic policy changes. Its most important metrics are slowdown and load, which will be explained further later on. Control points. So this is the third retro abstraction. What these do is actually to ease the enforcement of resource allocations in a distributed system. So a control point is really a point in the execution of a request where policies can be enforced. Control points are also executed locally at that point in time, and the configuration of a control point is done centrally from a defined policy. So as discussed earlier, these are the framework's main components. This is visually shown here: the workflows, the resources, and the control points. So, so what are some key points in this retro system architecture? As we discussed earlier, the key design principle is to separate mechanisms from policies. So what do we? Let's go a little back. So what do we mean by this, and how does this decoupling of these two items beneficial in distributed systems? For one, policies are easier to maintain as they evolve and change since they're elastic and dynamic. So this means that at the same time, this also means that policies are more flexible and extensible. So there are logically centralized policies, which can be considered a control point for distributed systems. Also, it eases complexities of writing policies and maintaining them. This decoupling is very important. So what are some features? What are some features of this retro framework? First of all, the measurement infrastructure for research utilization information across it goes across all of the distributed system. It has a logical controller. So what does really the logical controller do? What it does is it uses the resource library to produce load and slowdown metrics. Also, it creates policies to be used using these metrics obtained. Also, the current systems have hard-coded policies. Retro has dynamic policies. And also the enforcement mechanism to feed policies to control points. So a big plus, in my opinion, is this API library for Retro. So the advantages of having an API library here is to abstract the complexities of individual resources. Also, it's easier to manage the framework overall. Also, it has a resource agnostic scheduling policies approach. So what is agnostic in this context? It really means that it refers to the ability of a resource to work with various systems rather than being customized for a single system, which means that there's room for more flexibility from a resource perspective. So the design implementation, we're going to look at 4 items which have to do with resource measurement for workflow. So the first one is end-to-end ID propagation. So what this means is that when a request is started, Retro would produce a workflow ID, which will keep a consistent and unique ID by storing it in a thread local variable. So once this request is completed, Retro removes its association with the workflow ID in specific. Aggregation and reporting. So when it comes to this, the centralized controller in Retro, it aggregates the reports produced by workflow ID and resource, and it also uses the resource library to compute resource load and slowdown, which are essential metrics in this framework, as discussed earlier in the presentation. Also batching. So a system might actually batch the request. So batching really means to arrange the items in groups of multiple workflows into a single request. So when this happens, a batch workflow ID is created in order to aggregate resource consumption of the batch text in specific. For example, such as putting together the resources consumed when writing an H-based transaction logs to HDFS. That will be an example. Also, automatic resource instrumentation. So AspIQ-J is actually used to automatically instrument all hardware resources as well as the resources exposed through the Java standard library. So what is this resource library that has been talked about? What it really does is it computes the resource load and slowdown metrics, which are big important metrics in this framework. So let's look at the CPU factor when it comes to the resource library. So the resource library queries the thread CPU cycle counter when setting and unsetting the workflow ID on a thread to count the number of CPU cycles spent by each specific workflow, right? So therefore, what does this mean? The load of a workflow is directly proportional to its usage in CPU cycles. So what is this factor here as far as the resource library is concerned? The disk slowdown is measured by using a subset of disk I/O operation types that are monitored, especially read and sync operations. So the network factor. In this case, the load of a workflow on a network link is proportional to the number of bytes being transferred by the workflow specific. So the slowdown metric is measured based on its usage of the usage of the network. Therefore, actual network latency is not really measured, meaning that Retro, there's room for improvement when it comes to this. It can be extended in the future to implement a true slowdown measurement from the network perspective. So the thread pull factor here. When it comes to the thread pull factor, the load of a workflow on a thread pull is directly proportional to the total amount of time it was using threads in this pull in specific. So the locks factor, the locks operation. When it comes to locks operation, the queuing time of the lock operation and the time the thread was holding this lock, that's how it's measured. Therefore, slowdown in this perspective would be the total latency of the lock operation divided by the time that thread was holding this lock operation. So coordinated throttling. This is very important in this framework. So each control point is a per workflow distributed token bucket. Also, Retro keeps track of new control points coming and going, such as mappers starting and finishing, and properly as well at the same time it properly distributes the specified limit across them. So control points are essential to maintain coordinated throttling. Why? Because control points are checkpoints they're considered to be checkpoints for fast policy convergence and are allocated across HDFS, YARN, and MapReduce components. So let's look at the three main policies, the three targeted policies on retro. These are BFER policy, the RDRF policy, and the latency SLO policy. So let's talk a little bit about this BFER policy. So really, what is this used for? Really, it is used to throttle aggressive workflows and DOS attacks, for example. What it really does, the main goal is to provide bottleneck fairness across the system, and it also provides coarse grain isolation. So why does it do this? Coarse grain isolation implemented in this policy is used because workflows are guaranteed a fair share of the bottleneck resource. So the figure on the right shows the algorithm structure. Okay, so let's look at line 2 of this algorithm. In line 2, the slowest resource defined by S, the variable S, is identified based on the slowdown measure, the max slowdown, right? That we're looking at in line 2. Then the maximum fairness algorithm is used with demands estimated by the current load of workflows. We can see this actually in line 4, as well as estimating the resource capacity to relieve the bottleneck if there is actually any bottleneck. So what is the key takeaway of this policy, right? The key takeaway to understand is that the policy considers the slowest resource S, defined previously, to be bottlenecked only if its slowdown is greater than the policy specific threshold, which is defined. This policy is defined in the algorithm. So if this resource meets source requirements, this resource S meets source requirements, and if the fair share of the workload in question is smaller than the current load at the moment, then this policy would actually throttle the rates of the resource. Therefore, we can say that this policy only takes action, meaning that it would do the throttling only if there's a bottleneck in the system. If not, then it wouldn't get involved. So the RDRF policy. DRF means the dominant resource fairness. So also we're gonna look at the multi-resource fairness algorithm. This is really the key takeaway of this policy. It also provides room for bottlenecked workflows. And also its main goal, and really the main goal of this policy, is that it consists of a reactive policy approach. Well, so what does this reactive policy approach mean? It really means that the policy makes incremental changes and reacting on how the system responds to these changes. So it's a reactive approach rather than a proactive approach. So the slowdown measure, this measure is really to estimate the capacity. So this policy checks if the current slowdown exceeds a resource specific threshold. And when this happens, the policy reduces its capacity estimate to the current load. Otherwise, if the slowdown is within the threshold and the current capacity estimate is smaller than the current load, the policy increases its capacity estimate in order to cope for more capacity. So the latency SLO policy, the latency service level objective policy. This is the third and final policy of this framework. So the goal really is to achieve the highest throughput for L. L is the low priority workflow while meeting the latency targets for H. H is a high priority workflow. The key is to throttle L workflows as little as possible. Why? This is because if a workflow in L is not using an overloaded resource, it should not be throttled. Correct. So the evaluation, we're going to start looking at the evaluation of the retro framework. So the evaluation of retro, as we discussed earlier, is in the context of a Hadoop stack, right? So there's five open source systems. So we're looking at HDFS, we're looking at Yarn, MapReduce, HBase, and Zookeeper. So, there's workloads. There's workloads that cause resource overload. So some workloads that cause. So what really happens with these workloads is that it causes resource overload that are used and that are based on real world traces, and widely used benchmarks are used as well in this evaluation. So evaluation plans, right? Coordinated throttling is applied, as we discussed earlier. What it does is also let's start a little about coordinated throttling again. So this is applied in order to achieve bottleneck and dominant resource fairness, as we were discussing specifically in the BFER and the RDRF policies. So what happens is that it applies policies to resources of different types. So what are these different types of resources? For example, application level resources. We're also looking at resources shared between multiple processes and resources with multiple instances across the cluster. So also latency is guaranteed on resource containing workloads. Is definitely scalable. There's low overhead for a developer. Also, it does efficient throttling. So efficient throttling really it correctly detects bottleneck resources and applies targeted throttling to the relevant workflows and as well as the control points. So let's look a little bit into this the BFER policy evaluation in the Hadoop stack. So there's aggressive workflows that are introduced that are throttled without affecting other workflows, right? So this is one of the main goals of this policy. So there's a coordinated targeted workload throttling. This is really the proof. What is trying to be proven here is that there's coordinated targeted workload throttling. So we're going to look at three major workflows being introduced in this test. We're looking at sort, which is a MapReduce sort job, RW64M, which consists of 100 HDFS clients reading and writing 64 megabyte files with a 50-50 split, as well as scan, which is one of the three major workflows, which consists of 100 HBase clients scanning large tables. These workflows bottleneck on the worker machines. We're also going to look test with two minor workflows. We're looking at read8 KB, which consists of 32 clients reading 8 KB kilobit files from HDFS, as well as scan cache. So scan cache is going to consist of 32 clients scanning tables in HBase that are mostly cached in the region servers. We're going to work with a 32 node deployment in the Azure cloud. So each node in this 32 node deployment has 8 vCPUs, 14 gigs of RAM, and a 600 data disk over a 1 gig network speed. So if we look at the figures on the right, we see that in the top one, the disk throughput behavior. All right, so this is what's being measured here. So we see that the disk throughput changes as different workflows start based on the time that they're started at, and that the sort job declines steeply from the time it started to the time that other workflows started coming in and taking up the disk throughput, right? So ultimately, all workflows even out in this throughput usage in the green area, as we can see, and they get its fair share of usage, which is what this policy is really trying to do, right? So in the middle figure, we see the slowdown takes place on a few different resources, except the disk throughput. But the other resources only have little spikes. Well, they're not little. They're pretty relevant spikes. I apologize. Due to the fact that the workload burstiness takes us a lot. In the bottom figure, the usage ratio of for each workflow is looked at. So what is this usage utilization? In this case, is considered to be the achieved throughput relative to the allocated rate at a particular control point. So the latency service level objective policy. So this evaluation It consisted of an eight node cluster deployment. Uh, it's an end-to-end latency. The end-to-end latency SLOs across multiple workflows and systems, and the SLOs for both foreground and background text are evaluated here. So in this experiment, service level objectives are simultaneously enforced in HBase and HDFS for 3 high priority workflows with intermittently aggressive background workflows. So once these high priority workflows are normalized to the SLO's definitions, a background workflow temporarily increases its request rates, which will naturally, of course, affect the latency of these high priority workflows. So what do the results show really in this experiment with this policy? The result also shows a slowdown of different resources, such as, let's say, CPU and disk usage. So once the latency SLO policy enforces the SLOs of the high priority workflows, the background workflows are throttled based only specifically during the overload phases, just all over the overload phases. So RDRF and HDFS, there's 2 workflows that are being looked at here. Read4M, which consists of 50 clients reading 4 megabit files, and the list workflow, which consists of 5 clients listing 1,000 files in a directory by accessing the HDFS cluster remotely and sharing a 1 gig network link. We can safely deduce that the dominant resource in this case will be the network resource, since what is happening is it reads large amounts of data from the memory of the name node, which is the master, which as we know is the master controller in a Hadoop cluster. So the policy allocates each workflow the fair share of its dominant resource. In our case of this test, the dominant resource is a network resource, right? So in the figure to the right, we can see that the read4M task is started first, and the list task is started at time t of 5 minutes, as we can see in the x-axis as the time. So when the latter happens, when the list task is started, the policy follows the first read4M task in order to achieve equal dominant shares across both of these workflows. Ultimately, we can say that we wouldn't need to know the demands of these workflows, nor the capacity of each resource in order for our RDF to successfully allocate each workflow a fair share of its dominant resource, which is the network in this case, right? So what does this experiment show, right? This experiment shows that slowdown is viable as a proxy for resource capacity. So the slowdown metric is key here. And the reactive policies in this context work really well with the slowdown metric. So conclusions. We can definitely say that the retro is a proven framework for resource management policies in multi-tenant distributed systems. So it also provides key abstractions to decouple policies and mechanisms, as we discussed, is very important. There's a low developer effort, meaning there removes overhead, removes a lot of overhead of the developer effort to define these policies, and make them flexible based on their environment. It's a scalable and lightweight, right? So what is a scalable and a lightweight framework provide? It can be run into production. That's definitely essential when looking at these papers, right? Is making sure that these frameworks are scalable and they're elastic and they are proved to work in production, right? With big data. In the future, the control planes wouldn't be able to provide fair scheduling, prioritization, and load balancing. So this is still a work in progress, as we can see. So what are some personal comments here, right? The retro framework in itself it has solid features with a well-planned solution to its challenges, the specific challenges that have been pointed out earlier. It should not be designed as another orchestrator, more of a plugin, in my opinion, because there are too many orchestrators out there. We can see that in the Hadoop cluster, we have the name nodes, the master-slave architecture. So there might be, when we have these frameworks work together, there might be too many controllers, and that at the same time, we're looking at the redundancy of all these controllers, and and the more complex and the more redundant this 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 whole architecture becomes, there might be some room, uh, for mistakes, or redundancy in the efficiency of the whole architecture of the whole distributed system in itself. There's lack of flexibility. In my opinion, it's designed to work with Hadoop framework only, but there should also be an approach to working with other approaches like Dryad, using the direct acyclic refs, and other approaches that are out there when looking at distributed file systems. The scalability, in my opinion, as I've mentioned this before, is very important in the present and future distributed systems. As they become more complex, scalability is one of the main key items in order to make sure the distributed system is efficient, especially in production. So security, this paper hasn't really talked about too much security. So how secure it is to react to, let's say, hack attempts. So of course, this paper has mostly concentrated on looking at challenges where the distributed systems look at today, but as this framework becomes more developed, more implemented, I think the security perspective would be very important. As we know, cloud environments in the present are not too robust when it comes to the security perspective. So this is really a general problem, but I believe this framework should look at how the security perspective would be implemented into this framework, or how would it work together with other security plugins or in the Hadoop cluster if it will be ultimately implemented here. The authors in the paper understand the challenges of the present distributed computing, so that I believe this is very important because they really understand what's going on with the challenges. So that's why they were able to list the motivations, right? Multi-tenant systems. This is huge, I think, in future cloud systems. So the API library is a big plus in my opinion because a lot of developers really work off of API libraries. You can think of anything you want. You can think of OpenStack, right, which is what AWS is based on. This OpenStack cloud infrastructure as a service, right? So even infrastructure as a service, all the way to service as a service components, they all really have an API library, right? So this is really the approach that has been taken, and I believe developers will like this because it would be very familiar and relatable to them. And it also is open to be extended for the community. So I think once this framework really catches some more attention, and it becomes more of a big deal, the more it is evolved. I believe that it should be open and extended for other developers to extend this feature, this framework in itself, right? Thank you very much for listening to my presentation, and have a great day.